Hello, welcome to Spectra Forge. In this video, as a part of the Applied Digital Signal Processing series, I'll discuss linear convolution and its applications in real-world scenarios. More particularly, I'll take an example in wireless communications and explain you the real physical meaning of convolution. There are two parts of convolution, or there are two kinds of convolutions. One is linear and circular convolution. However, in this video, we will restrict to linear convolution and see its applications. In signal processing, convolution is a mathematical operation that is used to express the relationship between an input signal and output signal through a system's impulse response. What I mean by this is if x of t is an input to an LTI system, this a linear and time invariant system, then the output y of t is expressed mathematically through convolution, and the expression is given by y of t is x convolved with h of t, where you have an integration over x of tau, integration over tau from minus infinity to infinity for continuous signals. And for discrete signals, y of n, which is basically a discretized version of y of t, you end up you replace this integrand with the summation, and where L is the number of time samples, and so you'll have h of k times x of n minus k, or equivalently you could have x of k and x of k times h of n minus k. They are commutative, so it doesn't matter whether h of k or x of k comes first. So this is in signal processing. You might also encounter linear convolution in probability theory. So when you have a probability output y as a sum of multiple random variables, let's say y is x1 plus x2 plus x3, where x1, x2, x3, and so on and so forth are random variables of different probability distributions, then the final level outcome or final output is basically convolution of all those random variables. So but in signal processing, you have a different meaning for this. So for example, if in x of t is of length n and h of n has length m, then the output y of n will have a length of n plus m minus 1. This can be seen from the figure in the shown on the slide. So for here we have, let me bring the pointer. Uh, so here the s, if the blue line is x of t and the red square is the h of t, you flip the signal and do the time shift. So you will see the black line as the output y. You can see that this black line has is spread in time. So this has more sequences, or this length of a sequence is larger than the input length, or even the systems, the LTI systems length. So if blue square is the h of t, which is our system's impulse response, and red square is our input, our output is black triangle, which is the convolved output of the two squares basically, and it has spread over time. So this results extends beyond the original signal length. So it is, you can view this as spreading of our input signal over time. Okay, it may not be obvious, as in I think one might think that what is the point of having the linear convolution. I mean, invokes, it begs the question that the was the real significance of this. However, it should be understood that linear convolution has many applications, especially in signal processing. For example, in filtering or system analysis, image processing, or in audio effect, or in audio processing. So for filtering, if you want to design a high pass or low pass filter, which basically you have a x of t and you have y of t, and you want to allow certain frequencies, then you in some certain frequency in the output, then you have to invoke this convolution theorem or convolution formula, to design those filters. And system analysis. So if you also, I mean, for the same example, instead of the filter, you have a black box, which is what you want to analyze. Then for that you have to you have the output and you have the input. So the system is basically h of t. You want to analyze that system. So using convolution is what is invoked during this process. So similarly, image processing. So whenever we add filter to our photos, so we get desired, like if you want to have a blurring or edge direction or different features, like in Instagram you have multiple filters. So even to do that, you have to invoke the convolution and audio processing as well. So if you want to increase the bass or reduce the trebles, or different sorts of effects uh, can be made possible by invoking equalization. That's mainly the it's a basic fundamental mathematical operation that is invoked to do all this signal processing. Okay, now let's have a look at an example where linear convolution is useful, or we can understand the physical significance of it by by this example. So we consider wireless communications because it's easy to understand. So, for example, I mean, it's not necessarily wireless communication, but it could be wired as well. So it's any system that has an impulse response, basically. So, for example, yeah, let's consider these wireless comms, and there is a transmitter and the receiver, where the transmitter is transmitting a signal x of t, and this is going over the air, or if it's a wired communication, you replace it with a cable. It could be copper or fiber, and then it is received by the receiver, which is y of t. So this transmitted signal doesn't reach the receiver instantly and undistorted. Instead, it travels through a different propagation altogether. So this over the air channel, which is denoted by h of t, is can be pictorially seen in this here. So this over the air channel has, for example, here, this over the air channel is going through, the signal is going through multiple paths. So you could see this signal is just scattered or reflected by this building, and there is a house. So it has gone through different paths. So it will definitely not reach instantly and undistorted, because you have multiple signals, this is the same signal but arriving at different instance through different paths. So this can be represented in on a graph with time and its impulse response here. So this, you can see here that you have four paths, and you have a four Dirac deltas, which is basically four pass, I mean, four times, I mean, signals arriving at four different time slots and with different delays. So this is a delay 1, 2, and then you have delay 3 and delay 4. And the y-axis is basically the amplitude. So it's usually the line of sight, or the first timestamp will be having a higher power, because it has not going through any reflection or any scattering or anything. It's direct line of sight, which will have maximum power. It's not attenuated by any blockages. So these are the, but there will be significant delay. There may be a delay because of the propagation, because of the distance between the transmitter and the receiver. So that's the channel delay, and then there is a gain associated because of the distance. By employing, if you know the Friis transmission law, so the propagation loss will be inversely proportional to the square of the distance. So definitely there will be a loss. So the receiver is not receiving the signal as is transmitted from the by the transmitter. So there are certain distortions. So if you think of this as a h of t and is in our LTI systems, that means it is a linear and not time variant channel. Then we can write the y output y of n as the convolution of x of n and h of k. So this is what we have seen in the first slide, where I've shown for the discrete series. I mean, this could be written as x of k times h of n minus k, as well as as it holds the commutative property. So where L is now, so L is now the time samples. I mean, I mentioned L as a time samples. Here the L is represents the time samples of the channel. So you have L taps. So we are summing over the uh, L multipaths of the channel. So if we look at an example, so for example, since we have a four taps here, or four delays where the signal is arriving from, and let's call this as delta. I mean, let's take an example as this: h of t is delta of t plus zero point 0.5 delta of t minus 1, minus zero point 0.3 times delta of t minus 2 plus zero point 0.1 delta of t minus 3. So these are microseconds. Okay, so what does it mean? So this is called as impulse response of the over the air channel h of t. So this is how typical impulse response looks like, and this is the graphically shown here. This is the impulse response, and each spike here can be treated as an impulse. So you have a sequence of impulses here, and this is called the impulse response. So now, so h of t, what does it mean here? So you have a signal arriving at delta t, which is time 0 delay, or I mean, here I'm showing a delay, but there is actual delay. So if you consider the first path as a reference, then it is a 0 delay, and then you have 1 microsecond delay with an amplitude 0.5. For the first path, there is no uh, attenuation, for example. I mean, we can normalize that as well. It's not necessary that it will be 1, because definitely there is a proper path loss associated with the distance. So for the sake of explanation, or let's assume that this is 1, and you have 1.5, and then you have minus zero point 0.3 or plus 0.5. So the minus can be the phase, phase shift. So this is the channel response with 4 channel taps or 4 channel delays. Now the y of 0, if you look at the y of t at the receiver, you would end up with this expression. So if you substitute the values, so if you substitute the values for x and h, let's say you have 5 symbols coming in: x0, x1, x2, x3, x4, x5. So you're transmitting 5 sequences from x of t, and what is y of t receiving? So y of t at time 0, the first time sample, it will receive the x of 0 and h of 0. The h of 0 is basically the delta of t. That's what it is. I wrote here. So h of 0 corresponds to the first step. So it will convolve. The first sample will convolve with the first sample of the channel. And y of 1 will have the x of 1, the next new sample, times the first delay, which is delta of t, plus 0.5, which is because of this one. So you will see, because you have a delay because of the channel, so you see that you plus 0.5 times x of 0. See, so this is coming from the past symbol, the previous symbol. So the previous symbol has now arrived when I'm processing the first signal. So this will be added to the y of 1, and similarly y of 2, it will be x of 2 times h of 0 plus 0.5 x of 1 minus 0.3 x of 0. uh, y of 3 will be same thing. So this goes on until you will have y of 5 or y of 4, where you have all taps covered. So you will have interference from the fourth sample, third sample, second sample, and first sample by the fifth sample. So this is, if you expand, if you plug in the values of h and x in this expression, and you compute each values, you will end up with this expression. So what does it mean here? So what is the physical meaning of this? What's happening here? So we can see here for example, this every y of 1, y of 2, y of 3, the desired signals are x of 0. I mean, the corresponding signals, the desired signals are x of 0, x of 1, x of 2, x of 3. But because of the spreading that's happening, because of the convolution, as I mentioned previously, so as what did I mention? If you have a length L, length x, I mean m input and L input, the output is L plus m minus 1. So it spreads. I mean, the sequence is spreading. So because of the spreading, here you are seeing ISI. So in wireless parlance, this extra addition, other than the first row, first column, sorry, everything else is considered as ISI, which means it's intersymbol interference. So this intersymbol interference will distort my signal. So y of 1 and y of 2, y of 3, and y of 5, y of 4 and y of 5 has significant interference because you have more, I mean, many more symbols here, from many more symbols interfering because of the channel. So this is what we could see from the linear convolution. So the interpretation is, here we can interpret this as spreading over time. The original signal is spreading over time. So in this example as well, you can see the transmit signal is x of n, which has three taps or 3 points, and then you have a channel with 4 taps. So 1, 2, 3, 4 here, and then you have y of n, which is a convolution of x of n times h of n. So we plug in this expression that I showed you in the previous slide. When you convolve this first symbol with this one, and then in the second time y of 2 will be convolve this with this, plus this convolves with this one here, and then the third time you'll have this symbol convolved with this, and but these two will convolve with the channel tabs here and here. So and it continues, and it continues until all the taps or until all the signal is elapsed and it's spread in time. So the channel basically it's kind of distorting the signal and introducing by introducing the intersymbol interference. So what we do is we at the receiver side we have to have an equalizer which will invert this in convolution. So you want to convolve the y of t with inverse of h of t, or basically say filter. You design a filter so that it cancels or nullifies the effect of the channel induced interference. So this is one example where a linear convolution plays a role. So in typical single carrier communications, this is what happens. However, in OFDM, we have circular convolution instead of the linear convolution. That will simplify the problem to a greater extent, because implementing equalization in time domain, so this is in time, spreading in time, so it's a bit challenging for wideband systems, and it does complicate things. So in the next slide, in the next video, or in the next video, will next lecture or tutorial, we will look at the circular convolution and how it is different from the linear convolution, and what are the advantages of having circular and linear. Do we need to have both, or why? But in general, everything is a linear convolution. So the so any system x of t, when it goes through a black box with an impulse response h of t, the y of t will always be linearly convolved with linearly convolved with the system's impulse response h of t. So the y of t will be x of t convolved with linearly convolved with h of t, and we'll see circular convolution in the next slide. Until then, thank you. And if you have any questions, please comment in the section, in the comment sections below. I'll try to answer them in the next video. Thanks.